Thanks for coming. I'm going to talk about deep time access for robots, and I probably need to explain to you what it even is, because I made it up, right? So this is a concept I'm introducing to make a point about what the difference is between systems like AlphaZero that play Go at a superhuman level, and what we do in robotics, and why we haven't solved robotics with something like AlphaZero. I'm going to introduce a bunch of concepts, and most of the talk is going to be concept after concept after concept, and I'm just asking you to follow along and bear with me on this. It will make sense eventually. Okay, so let's start with looking at the world in a particular fashion. Let's treat it like the totality of all dynamics that are out there, right? Stuff happens. Things influence each other. There are causal chains or more causal networks. They're all interwoven. So the world is a bubbly thing of stuff that's going on, right? It's all dynamic, so it sort of develops over time. And time is really nothing particularly mysterious in this view of the world. It is really just a way of indexing the dynamics, right? Stuff is going on, and then to make a difference between what used to be the case and what's the case now, you have a time index, you up it by 1, and something has changed. So let's assume time is just telling the difference between what was before and what is now in the dynamics of the world out there. So when you say, time has elapsed, you really say something has changed in the outer dynamics. And to illustrate this point, you could, in this non-mysterious way of talking about time, say that clocks are actually devices for creating time, right? They make something happen when otherwise nothing else happens. So time has passed and the dynamics of the world has progressed some. Okay, and then there are patterns in time, right? So the dynamics, they bubble, and then there are things in it like squirrels or whistles. So I'm referring to the sound, not the little object, or stones. And these are stable over time, right? There's a squirrel, something happens, squirrel is still there. There's a stone, something happens, the stone is still there. So some of these patterns are more stable than others. You will notice that stones last a lot longer than squirrels do, and squirrels last a lot longer than the whistle, like the sound. It goes away, it dissipates in time, while the squirrel sort of remains there over time as the dynamics progress. And the reason that is, the cool thing about squirrels is that they adapt to the environment dynamic. They have a system spotter. They know what is part of the squirrel system, and they know what's part of the outside world, and they try to keep the squirrel intact, right? Whistles don't do that. They just dissipate and devolve and go away over time. They have no internal dynamics within the whistle system that stabilizes the whistle. Squirrels do. Squirrels know what what they let pass through their system spotter. Right? They eat a nut or drink some water, and they do this very deliberately. Other types of systems or other types of patterns in time, like a whistle, don't do that and don't have that way of self-stabilizing and keeping the squirrel system intact. Okay. So systems adapt to their environment, everything that's outside of the system, at different timescales. Some take a much longer time to adapt than others. Like the squirrels are pretty fast at adapting to their environment. They're hungry, so they need to keep the squirrel pattern intact. They don't want to starve, so they go dig up a nut and have a snack. Right? A tree doesn't do that as much, right? They can't move about. They can't really prepare for a dry summer by going to a wetter place, right? And you can tell that by looking at the woods in Germany right now. So some systems are quicker to adapt to the environment than others. And that's because they have more internal dynamics available to predict and work with the outside environment and to sort of know what's going to happen in the outside world, adapt to that before it happens, and then they're going to survive a harsh winter by having stored some nuts. Okay. So now the universe is a large and chaotic place, and squirrels are rather magical, right? So there's a little animal, and it puts away some nuts for the winter, and it survives the winter, and that's really an astonishing thing in this totality of bubbling dynamics that the universe essentially is. So how do you make a squirrel when you're a universe that doesn't know what it's doing, when there's just bubbling dynamics? How do you find a squirrel, in other words, in this huge dynamic system that the universe is? So you have essentially three types of search that you are applying. First of all, you do random search. In all the totality of the universe, there's at least one, we know there's one, planet Earth, that has conditions for squirrels to show up. We don't know if there are others, there might be, but at least the universe has thrown enough matter outside so that one planet, Earth, will happen to be a very friendly place to squirrels. That has happened. And lots of other places in the solar system and in the galaxy, and in all the other galaxies and in all the clusters, may or may not contain squirrels, but at least we did this huge random search to find one place where it's the case. Okay, and then you have Earth, and then you do some evolution. Now that's a more directed search, right? It starts with bacteria, and they may have happened randomly. And then the thing to stabilize your system's pattern self-stabilizes itself. So you have like a system that adapts to the environment using evolution. And it's a very slow and painful process, and it takes a very long time to produce a squirrel, but eventually it does. And there's a squirrel, and it's very well adapted to the environment of my garden. And then finally, the squirrel does something, and it cheats again. It's even faster at adapting to its environment. It learns. It uses some of the internal dynamics that has been created by random search and evolution. Right? It's a very complex system, a squirrel. It uses some of that internal dynamics to remember where the nuts were and to learn that it needs to do that, or at least to learn where it kept them, so it can survive a harsh winter. So learning, again, is sort of cheating evolution, like evolution was cheating random search, by having faster time, right? Time runs faster when you learn than when you do your evolution, than when you do random search. We're accelerating for real on this planet. Okay, and now intelligence. Yep, the squirrel is showing some intelligence, as do trees in their evolutionary adaptation. Intelligence is the ability to adapt quickly. Right? We say something is intelligent when we are impressed by how fast it adapts to keep their system boundaries intact to a changing environment. So intelligence is access to time, access to internal dynamics that can keep the system boundaries intact. That's what it really is, right? Random search and evolution are much slower and are lesser forms of intelligence than the learning that we see in squirrels or, in fact, humans sometimes. Okay, and how do they do this, right? What do they do with their internal dynamics so that they can adapt quickly? They simulate the external dynamics. They take a part of what's going on in the outside world, make a predictive model of it in their heads, the little squirrels, right? They can predict where the nut will be in winter because they put it there and they remember it. So they take a bit of their internal dynamics to reproduce what's going on outside. So they build a little simulation. And coming back to time, this means you can say they create additional time for themselves, right? They can think things through in their head. They don't have to act it out in the real world to find the nut. They don't need to go to all the places. They can actually do this in their head and say, this one I've already eaten, so I don't need to go there. I can go to the other one. So they simulate the action in their head, go there, and have a snack. Okay, and now coming back to AlphaZero, and now it sort of, I hope, comes together. AlphaZero has deep time access. Deep time access means it has access to more than a single channel of time. Because what AlphaZero does, okay, I should explain what it is for those who haven't been here in Jonas' talk earlier. So it's a computer program, an AI, that learns from knowing nothing about chess or Go, and plays it as a superhuman, at a superhuman level. It does this by playing games against itself many, 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 many times. And it discovers sort of the patterns of this environment and masters it much better than humans can do. And we've seen the video earlier. So the key for AlphaZero is all the dynamics that it needs to adapt to are on the chessboard or on the Go board, right? There's nothing else. Nothing surprising happens on a chessboard. Otherwise, it wouldn't be chess. So again, access to deep time means you can parallelize rather than having to act out on the chessboard what you're trying to learn. You can perfectly simulate chess, right? That's the nature of the game. The reason chess is so, or games in general are so satisfying is the dynamics that we're up against in those games are completely understood and very well predictable, right? It's just completely constrained. Nothing crazy happens. If you have a structure like that, you can simulate it perfectly. You put it into a computer, and then you just throw CPUs at it. And that's what I did at AlphaZero, right? You throw CPUs at the problem, meaning you can essentially play all parties of chess against yourself at the same time, and you get superhuman intelligence instantly. This is what deep time access means. You do not have to, like a human, right? A human player, when Magnus Carlsen plays chess, he has to play it on the board. He can't parallelize. Oh, he sort of can, right? 15 games, 20 games, but he plays worse when he does that, and he's probably not learning while he's doing it. But otherwise, other than that, he has to play it in real time. AlphaZero doesn't do that. And that means this is a fundamental new quality. After random search, evolution, and learning, deep time access means you can jump to superhuman performance instantly by just throwing compute, CPUs, at the problem in an environment dynamics that is completely simulatable. Now, luckily, AlphaZero doesn't live in the real world. Robots do. So AlphaZero can't solve robots. We do not have a simulation of the real world, not even close. In fact, a good simulation of the real world is a map of the territory at the scale of 1 to 1. If you simulate the real world, you build the real world, and you might as well live in that world and improve it directly, right? The complexity of the totality of all dynamics is really very complex, and you can't do it. So you need to cut things out, right? This is different from a board game, which we invented to have satisfying, easy dynamics. We need to learn what of the dynamics in the real world matter for our goals. We need to build a system that can extract these dynamics like a squirrel does. Not everything that it sees or experiences matters for storing nuts. The precise shade of the sun when it was hidden probably doesn't need to remember that. It doesn't remember, it had a fight with a crow on the day earlier. None of this matters, right? So you need to be able to select what of the environment dynamics you need to simulate to survive and stabilize your system borders. Okay. This also means working on better simulations for solving robotics is a dead end. You can just add stuff in your simulation, but you essentially tell the system what it can learn by doing that. But you're really making a judgment of whether it will be relevant for the system. And in fact, anybody in the room who's a gamer knows this, right? We got very good at simulating the pixels, how the world looks to a human. But we all know the actual dynamics are very, very poorly simulated in games usually, right? Enemies spawn on the ground and they get teleported. The world doesn't work like that. And if you adapt to this in the game, you're cheating well, but it doesn't really tell you anything about the real world. So we can't just simulate our world, our way out of the robotics learning problem. So, okay. Herbert mentioned my company, Micropsi Industries. What we're doing is we're sort of building the best generic robotic learning systems that you can buy today. And they don't learn in simulation. They borrow time from humans. They use our ability to tell what's relevant to simulate in the world, to build predictive models of their environment, and work with that to achieve solutions in the industrial space, right? We're building fridges and German machine bow, essentially. So we borrow human time, and we borrow human experience of what you need to simulate to make an informed decision, to make an intelligent, adaptive behavior in a human. Did I click? Okay. So that also means robots don't really self-stabilize. They're not really alive in the way a squirrel is alive. And we know that, right? What they're actually stabilizing is the human system boundary. They build cars for us, and that means, in a dark winter night when I'm hungry and I need to get food, I can get in a car and not freeze to death in a snowstorm. And that's been possible because a robot built an affordable car for me. So right now, humans inherit our sense of relevancy of the environment. and they bear their name with some right. They're really robots. They're our slaves. They do our bidding. They stabilize our, not their, system borders. We kind of like that. Okay, now how would we make them alive, should we want to? Somebody is going to want to eventually, right? So how would we do it? The best AI systems today aren't engineered by humans. We don't sit down and think, how does intelligence work, and how do we decide what to simulate for this system to build a meaningful predictive model for its environment? We don't do that anymore. We search for functions in function space. So, bit of illustration, right? The squirrel function is a function that it has lots of parameters, and you input whatever the environment does for the squirrel at some point, and then you run the function, you up the time index by 1, and you get the behavior of the squirrel on the other side, right? Instead of trying to engineer a squirrel, what we're today doing in AI is typically we engineer a system that can search for the squirrel function in the space of all possible functions. Right, that's many of the sort of successful AI systems that we've heard about today even are hyperparameter optimized in large grid searches for good hyperparameters. Okay, so before we talk about how to actually do it and or whatever I believe I know about actually doing it, what happens when it happens? What happens if we do it? Things get really, really freaking serious, because that means we unleash this new timescale that we have generated with access to deep time, with parallel multi-channel access to time, onto the real world, right? That's the relevance of robots. That's why robots matter. You can solve all board games. They never make it out of the board game dynamic they have been developed for. But robots live in the real world, and if you solve the problem for the real world, if you solve the problem of selecting the dynamics from the environment that you need to adapt to your, to self-stabilize your system, then everything that came before becomes part of the landscape, like trees for us, right? They have been around for a long time, and they're still around, but action-wise, they don't really matter. They adapt so slowly that we stop thinking about them even. So once intelligence is happening on the planet, trees stop mattering as adaptive systems, as agents on that planet. And pretty much the same is inevitably, right? We can talk about alignment and all that sort of stuff for ages. But the moment this problem is solved, by the moment some system finds this function in function space, our timescale becomes irrelevant. Everything happens so fast, we're just part of the landscape for the new systems that will then work the Earth. Okay, so should we want to make it happen, and by the way, I don't know how to make it happen, otherwise I would probably be in danger and much richer than I am. So what we probably would need to do is to constrain the search space, right? This search space for squirrel functions or for intelligent functions, functions that can select external dynamics to reproduce and predict, is very large. So what we probably want to do is build a system that can perform this search and constrain the search space in a way that we might, in historic time, hit upon a squirrel function or an intelligence function that can select environment dynamics. We probably want to resist the temptation, I'm sort of speaking to my own past here, we probably want to resist the temptation to engineer the target system, to think about, okay, how does intelligence work? And we need to cut open a squirrel and then understand all the neurons and then build a model and then we do fMRI on it. And then we sort of rebuild it from having looked into the system. I don't think that's going to, we're just too dumb to do that. I don't think that's going to lead to success. We probably want to engineer the search. And in a way, the things that Jonas has presented earlier today is very clearly a first step towards doing that. Engineer the search. So we have built systems that can start to look for the intelligent function in function space. Okay, that's all I had, and we have, as planned, 10 minutes for Q&A. On what we do with robotics. Thank you. Or on what I've just presented. I hope it wasn't completely incomprehensible.
Ronnie. So, okay, I start there.
I have a very nice presentation. simple question: what happens if you randomly change the boundary conditions or the number of parameters in an unpredicted way? What does this ground zero, how you call it, does? So I understand that for industry applications this might help, but if you want to predict something, for example, how the climate will behave, if something completely unpredicted happens, then I think this model does not help. But
yeah, okay, thank you. I think let me try to go there and see if that's helpful. So in the very zoomed out view that I'm taking, right, completely unpredicted conditions, so the environment boundary changes completely, are just another way of, this is just more dynamics. And obviously, there is going to be dynamics that you're not prepared for, right? So have you evolved or learned a type of metacognition that will allow you to adapt to that? You better have if that happens, right? So you're asking exactly the question: what happens if the rules of chess change while I'm? Yes, yeah, okay. And AlphaZero is of course completely clueless, right? You introduce a new piece. You come up with something from Star Trek. No, they just do it in 3D. You come up with a new piece and it can do things that it has never seen. It is completely clueless and it will fall apart, necessarily. Magnus Carlsen would be better because you could explain the rule to him and then he could adapt. And that's sort of my point. He has adapted to a much wider range of environment dynamics because his life isn't just chess. A large part of it is chess. But his life isn't just chess. So he has built more intuitions about how to adapt to more unforeseen stuff than AlphaZero will ever have. And that's why AlphaZero solves Go and chess in such a satisfying superhuman manner. It can concentrate on something that's completely and utterly constrained and completely understood. Should this make us humans sort of feel slightly smug towards the AIs? I don't think so. Because our environment is changing rapidly, and there are some indications that it's changing more rapidly than we can adapt to, individually or as societies. Right? The jury is still out if we can do this. We are behaving like it's the 1900s, and what's worse, we don't even know what to do. Right? Some people will claim, and they will be very loud about it, but they can't show a convincing trajectory through climate change. Right? We don't have that. We're sort of just making stuff up as we go along and hope our predictive capabilities and the sort of access to time that we have mastered by this time, for instance, by building very large compute clusters and running simulations, is enough to evade the cataclysm that's coming there.
Do we have another question? Okay, there's one. All right.
Try and be loud about it. So what we're trying to do is basically not finding the intelligence function, but finding any function that would replicate the output that human intelligence has created in form of text or imagery, right? So, and then the hypothesis is maybe a function that creates a similar output than the human adaptive intelligence function that extracts meaningful concept out of the world is in some way comparable to that function. But we're not really directly looking for that function, right? Would you say that kind of makes sense, or would you go different about it?
No, I agree. The language and image-based world models that we've now extracted from the internet are really a way of capturing a large part of sort of the collective human wisdom and what we know about the dynamics, and it works really well. Now, it very clearly doesn't think, and it doesn't know how to incorporate additional facts, right? We can just run the same thing against Reddit again in a couple of years and hope that humans have come up with something. Or we can sort of pipe it back into itself and hope that something meaningful comes out of it. Whether that will happen is hard to tell, right? There's this joke where people say it's just a statistical parrot. and it just regurgitates what everybody is saying. And then the answer is, yes, your mom is just a statistical parrot and just regurgitates what's been said. And something we're all your mom, right? And sometimes she will hit upon something that is genuinely new and helps. And it's much more random than we think, right? Maybe we're all just babbling things that we heard on the internet. And at some time, and as we also act in the world, we sometimes act on it, and sometimes it makes sense. And there's a huge deal of survivor bias, and we get it right almost by accident. And we look back and say, "Oh, it was me. I was very clever here." And it actually never happened. And we're just adapting not because of our cleverness, but because we essentially do random search as a culture on those kind of memes that transformer models today predict.
Okay, Philip.
I mean,
they all were.
I mean, it's clear. I mean, foundation models are trained on the internet, which is something we wrote, right? And obviously, the next step, there's always a question: how far can you go there without training something on the real world, right? Because as if you had only, read things, how far can you get with an understanding of the real world? But as soon as you go to the real world, it's very hard to control, right? You can obviously just, let a robot run around, perhaps with a body, depending on whether you wanted to have some type and try to learn, but you just don't know what it will learn.
Yeah, and you can't do it in real time, right? I mean, this has been tried, right? Google put 15 robots in the basement trying to do reinforcement learning on gripping behavior. And they got a mildly interesting demo out of the 6-month experiment, which was very expensive, right? Doing this in real time just makes no sense. Humans are good at it, and it takes us 40 years to get any decent mastery of most things. Sorry for the younger ones. The right age is exactly 43 years. So not only is it hard to control, right? We'll learn any random thing. Also, it will take ages. We won't arrive anywhere. So we're really not looking for, and I tried this in my sort of research entrepreneur past. You don't want to do reinforcement learning in the real world. It's just a dumb idea. It takes too long, and you deliberately insert noise into the world. It's just not going to go anywhere. So you need to do it in simulation. Now, the problem with the simulation is they're really hard to build, and they're really hard to run. And understanding what part of the environment dynamics is relevant to your particular problem is completely unsolved. Nobody knows how to do it. With all the excitement of the transformer models now, this is an approximation, right? It's a cheat, and it's a very good cheat because we're using sort of the collective knowledge of all the world's culture, which is sort of amazing, right? If you say it like that, about what the world does and is. And some world dynamics is captured, and it's very well adapted to how humans interact with the world, right? This is all in there. But it doesn't apply to a robot body, right? It's very different. It needs oil and not water, and we all know this from Robbie Tobby and Das Flievertüt. So, these are different bodies, and you can't really just throw any of those models that we have against the real world. You need to search for the squirrel function in function space, and we don't know how to do that yet.
I think you touched upon it, but could you define intelligence?
Yeah, I had a definition in there. It's necessarily incomplete. So it's a very colloquial one, right? We say we observe intelligent behavior when we see a system that wants to self-stabilize, adapt to its environment quickly. And quickly is obviously a very relative term. But, I mean, trees are more intelligent than stones. And squirrels are arguably more intelligent than trees, and we're doing a bit better. So in my sort of colloquial definition, you get intelligence is access to time in the sense of ability to internalize external dynamics. You have enough internal complexity to sort of build a predictive model of external dynamics. And the better you get at this, the better you get at selecting what to simulate, and the more compute you have available to do the prediction, the more intelligent you're going to be.
I have a follow-up question, perhaps about the concept of the time that you had for zero, because I wonder, what about the training time? As a human, I actually when I'm in front of a new problem, I do the simulations of the real world on the flow, and then I test them, check whether they're working or not, and then I actually adapt the simulations. And now when you have the deep time in the AlphaZero, if I got it correctly, it does the decisions instantly, or doesn't do it, or how does it work? Because you didn't incorporate the training time, did you?
Yeah, so the scary thing about them, I mean, the inference time I'm not so interested in, right? Whatever compute they have available and how well they parallelize this, and okay, you know, maybe it thinks for 15 minutes. If it does the smartest thing ever and throws the best human players off, I'm still going to be impressed. The cool thing about AlphaZero is the training time. Because, I mean, they didn't literally throw every CPU at the problem, but in a principled manner, they could have done that, right? And then you can parallelize most of the iterations that Magnus Carlsen needs to do, right? And that's the scary bit. That means whatever system has that capability of having a simulation of its environment dynamics where it needs to perform, that is so faithful that you can just roll it out in space on compute. You are going to get a system that adapts to this particular environment much better than anything we humans can field.
Thanks. So it does the calculations at time. It does not have a huge database or something.
No, actually, no. It observes the board. It just sees what's on the board, and it comes up with a superhuman move every time, after having played more parties of chess, more games of chess than any human has ever played. And it can do that in like 2 days or so.
Okay, thank you for the answer.
The times of what you're referring to is sort of the old school of doing computer chess, right? Where you just had a huge library of everything that humans ever played. And I think to a degree, I mean, AlphaZero doesn't do it. That's why it's called Zero. I think the previous versions of that did some of it. They just wanted to win at chess. And then AlphaZero was sort of the proof that it's game over for the humans because you can actually learn everything you need to know without looking at the databases and the history of chess or Go.
Okay, thank you very much. Maybe just one comment that I really thought of now. So like creating a simulation of the environment. So and how do we move forward now in terms of these AI models, large models that we had. So what I found very interesting, and there's this recent podcast with the founder of DeepMind and I think Lex Friedman on the DeepMind protein folding thing. And it's so fascinating that you start with simple games with very precise rules like in chess, and there's no big complexity in that environment. And you start training systems and you come up with first models, and then suddenly, I mean, you get into physics like protein folding. Now they get into many other physical, like very fundamental systems, and they build predictors for this behavior, and they work incredibly good. And from that, you go step after step, and you stack up an environment that's ever more powerful to simulate more complex environments. And I think, I don't know where this gets, but this is super fascinating to see that it's happening exactly now. And I don't know, like going sci-fi-esque into the future, you know, you have this Elon Musk's statement where he says, you know, there's no chance we as humans, I mean, we become the environment and irrelevant unless we merge with it, yeah. And that's his crazy Neuralink idea. And I don't want to scare people, but I think in that staging from getting ever more complex in what we can simulate and becoming irrelevant in terms of timescales, etc., that might make sense somehow, like in theory.
Yeah, it does. And last remark, and then I'll vacate the stage. The area of the most complexity is actually where we live, right? The reason it starts to work at the very high end, cosmologics and models of the universe, and the very low end, is that there isn't much complexity there because you have very few pieces on the chessboard, right? You understand the standard model of physics and you sort of know how to simulate it. As you aggregate and as the sort of causal nexus becomes crazier and crazier on top of that, you get a sort of a layer, a zone of complexity where squirrels live and us. Right, and this is hardest to simulate. We might think, right, the very large or the very low is the hardest, but it's actually us. It's here where all the magic happens. The rest is building blocks put in place for by the creators of the universe for the great random search for squirrels.
Okay, thank you very much. So let's end with this. And I think now we have a lunch break, and around 1 p.m. We continue. Thank you for being here.